Welcome to the Australian Water School, the home of demand-driven industry-designed training for the global water sector.
Welcome to another great Australian Water School webinar. Today we're going to be discussing tsunamis, dam failures, and non-Newtonian modelling. This is really going to be interesting. And with us today, we have a fantastic team of very experienced modellers. You can see on the screen there, Greg, Shuang, Bill, and Chris. I'll be chairing Trevor Pillar, and the home base for Australian Water School is Renee and Joel. So look, thanks for joining us. It's going to be a fantastic time. We'll get straight into it. I can see so many, nearly 40 countries have joined us today across the globe. Must be very late in some parts of those places, but we really appreciate you taking the time to do this, and I know it'll be worth your while. Greg, Shuang, Bill, and Chris, thank you so much for joining us, guys. It's just fantastic from all over Australia, actually mainly East Coast, I understand. Yourself first, Greg, you're up in Queensland?
Yes, sunny Queensland and lockdown-free Queensland, I might
add. Good, COVID hasn't got you. And yourself, Shuang? In the same location?
Yeah, same location, but I've locked myself in a webinar room.
Good, great to have you, Chris and Bill, up in Queensland as well.
Queensland, yeah.
All Queensland.
Not locked in a webinar room, though.
No, it's great news.
Only locking Shuang.
This is a team that I can vouch for. We've been together for many, many years, and their work is second to none. It's going to be a fantastic webinar. I won't waste too much more time on the introductions, except to say the conference on your screen right now coming up next week, TUFLO UK Europe User Conference, 21st, 22nd of September. Change in a changing world. It's live, but not being able to get to the UK won't stop you. It's also online for the first time, so that's fantastic. Join that conference if you can. That'd be fantastic. Go to the website and you'll pick up the details. All right, shall we get cracking? It's going to be Greg and then Shuang, and back to Greg again, I understand. And in the background, Bill and Chris are going to be hammering away with question and answer. So over to you then, Greg. Take us through this. This will be fantastic, and Shuang, it'll be great.
Okay, very good. Thank you very much, Trevor. Now, I have, Shuang and I have put together quite a comprehensive presentation, so we are going to have to step through this at a reasonable cadence to get through it in time. We're going to talk about dam failure and tsunami inundation, and just to look very, very quickly at some of the theory behind it. And then we'll talk about, in particular, dam failure modelling with some benchmarking on that, and tsunami inundation modelling, and again some benchmarking, and then we'll move on to non-Newtonian flow and some benchmarking of that as well. Some of the characteristics that are common to tsunamis and dam failures are particular that it's a highly transient phenomenon, and initially it's with both a dam failure, when the wall initially collapses, it's quite three-dimensional. And likewise, when you have a deep ocean earthquake, the initial wave development can be a bit three-dimensional in a deep ocean. But once the wave runs up onto the continental shelf and approaches the shoreline, it quickly transitions into the regime of shallow water equations, where the wavelength is greater than the depth. And likewise with the dam failure is that after the initial wall collapse and the flow is really starting to spread out down a valley and along a floodplain, then that becomes quite two-dimensional as well. Very transient phenomena, rapid changes, often regimes of both subcritical and supercritical flow with hydraulic jumps in there. And particularly in the case of dam failure, you've got some of them are hydro dams that are just full of water, and others might be a tailings dam for a mine site, which can be full of mud, in which case you've got a very non-Newtonian flow. Whichever way you look at it, these are terrible events, catastrophic events. In many instances, a significant loss of life and a significant loss of property as well. So the better we can plan for these, the better everyone in the world will be. Just quickly, your 2D shallow water equations there. The very first term on the left is your local derivative for velocity as a function of time. And then we need to include gravity in that as well to give us some acceleration. The first green circle is the advection of the momentum. And then the second green circle is bed resistance from the bed friction. Then the third blue circle there is the turbulence, the eddy viscosity term, and I'll explain why that's important later on. For these sort of models that are generally short time scale and generally not huge physical scale, we're not talking about modeling tsunami propagation around the whole planet. We're talking about localized effects once the wave runs up onto a coastline. Including atmospheric pressure terms are really just not necessary, and likewise external forcing from wind isn't needed either. The only other one in there that could be included is Coriolis force, and I think there's a reasonable argument that for most of this modelling it's not necessary, either because the physical length scales are so short, or else because we're not talking about the actual physical movement of fluid over thousands of kilometres to changing latitudes. It's a very localised movement, short, it goes back and forth. And so the Coriolis term really cancels itself out again after a short time. In the animation on the right here, we're just showing the results out of a model where you have a tsunami inundation onto a urban coastline with a whole lot of buildings built right up to the shoreline there. And the very first thing you can see from that animation is that it's highly transient. This is not a steady state problem, and it cannot be solved with a steady state solver. You need a transient solver. But as discussed before, there's also hydraulic jumps that can happen in there. So you have shock capturing is important. Capturing the actual height of the waves that propagate through on land is very important, and that generally requires a second order scheme to get that nailed right. You need an appropriate mesh size. Generally, you need a reasonable resolution within the urban environment, or in the case of dam modelling, within the river valley and any towns of interest. But then you want to be able to coarsen that mesh out in regions that are not so interesting. So, the flexible mesh is really useful, or an adaptive mesh size is very useful. The physics, again, as I said, transient with hydraulic jumps. Generally, to capture what's happening in detail, you also need small time steps. So, using solvers that use an implicit matrix formulation and solving over, a Courant number of 10 or 20 is not necessarily what you want for tsunami or dam break modelling. You generally, an explicit solver is what you want, and small time steps to capture the detail. And of course, the accuracy of the solver. You need to know that the solver is actually going to give you sensible results. And it's one thing to do the maths and code all the maths, but it's another thing to actually benchmark that against real world simulations. So that's one of our mantra at TwoFlow, is just test, 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 find benchmark models that have been published, and make sure that our solver reproduces the results. We have a couple different software packages that can do dam failure and tsunami modeling. We've got the standard TwoFlow software, or the HPC, which is the GPU variant. And then there's also TwoFlow FV, which is probably one of our lesser known products, but also a very, very powerful engine. I've just captured there the common features of each solver, which are pretty much everything in blue there, and the pink is the difference one. So in TwoFlow, we've got the standard HPC solver. You can either have a regular grid, or you can have a quad tree grid with adjustable mesh size, and Shuang will show you some more examples of that later. In TwoFlow FV, it's a fully flexible mesh, triangles and quadrilaterals. The standard TwoFlow HPC uses an explicit fourth order temporal solver. Whereas TwoFlow FE, although it's a first order solver, it actually offers a mode split option, which is particularly useful when you've got the tsunami propagation from deep ocean up onto the continental shelf, because it solves the deep wave propagation separately to everything else. And both of them have got adaptive time stepping and very, very fast engines that run either multi-core CPU or to run on GPU. Okay, so let's talk about some dam failure modelling work. The first example we've got here is a one-dimensional problem that's got an analytical solution from Stoker. The second example we're going to talk about is a two-dimensional problem of a dam breach into a channel that's got a building obstruction in the channel. And then the third example we're going to discuss is the Malpasset dam failure in France from 1959. Okay, so looking at the one-dimensional model here, what's really important is this analytical solution from Stoker assumes hydrostatic pressure. And that basically means that it's not going to capture the initial collapse of the wall very well. But beyond that, it actually captures everything else quite well. So we've got a step change in water depth here from 10 meters down to 5 meters at time 0. Then you remove the barrier that's holding the wall of water back, and then you let it propagate. And you'll get a kind of a half-height shelf that propagates to the right with a hydraulic jump there, a steep wall jump on the right. And then you've got a sloping wall acceleration of flow on the left. And as time goes on, then those two waves spread apart in the two different directions. Importantly, if we draw some lines there marking the demarking the transitions of depth there, we can calculate that the very left line is going to be traveling to the left at the wave celerity speed of root GH0. The next line at the bottom of that shelf propagates at the speed given by that equation there. Now, I haven't gone through all the details of the maths. This is straight out of Stoker's paper. Then we've got U2 is the horizontal velocity of the intermediate shelf of water that's now flowing to the right. And then we've got the velocity of the wall there, which is actually, the hydraulic jump velocity is actually different to the fluid velocity behind it. Then we've also got the velocity, the wave velocity in the shallow water to the right. You can combine all of that together to eventually get a solution that you can solve for all the different wave speeds of what's happening in there. And really the point of this is quite an advanced mathematical model. Interestingly, when we actually test this with our software, by applying those equations I showed you on a slide further back, on a cell-by-cell basis and capturing physics, which is continuity of mass and continuity of momentum, once you capture all of that and do it properly, then it actually reproduces the solution just fine. So this is at time 0, and we've got two different lines there. The dotted pink line is the analytical solution from Stoker, and the solid blue line is the result from the two-flow HPC solver. And that's at time 30 seconds, and then at time 60 seconds, and you can see the agreement is just absolutely spot on. Now, this is using a cell size of 1 meter, second order solution, and a Coulomb number of 0.5, and that's 90 seconds. Okay, now when we run this with some different cell sizes, we've got plotting 3 different sizes there, the blue, the green, and the black or dark gray. The dark gray is at 20 meters, which is starting to get quite a coarse cell size, and we are actually beginning to see a little bit of blurring of the edges of the solution on the left-hand propagating wave, and also we're seeing a little bit of a numerical artifact in the hydraulic jump at the right-hand side there, which is a function of the second order calculation. In two-flow HPC, that second order calculation is tuned quite highly so that it tries to stay second order for as much as possible before dropping back to a first order solution. And that's giving that little edge at the edge there. We can run the same model in two-flow FV, which is our flexible mesh solver. And in particular, its second order spatial solution is tempered with a gradient limiter, which prevents that little artifact from happening on the hydraulic jump on the right-hand side. Although I think the price of that, as you can see on the left-hand side, it hasn't quite captured the sharp edges there that you can see it on the analytical solution. But overall, it's still a very, very nice solution. There's quite a few differences between what happens between that analytical solution, which assumes hydrostatic pressure, and what happens in real world. If you run this model in a full 3D CFD software, which is the red solution you can see there, which is from Flow 3D, and the crosses are actual experimental testing work, you can see that when you solve for this with the full 3-dimensional set of equations with no hydrostatic pressure assumption, then you get a different result, and you can use a computer to get the right result. You know, that red line from Flow 3D is showing us that, but it is a little bit different to what happens with the 2D solver. So that goes back to what I was saying earlier about the initial collapse of a dam wall. If it's an instantaneous failure, you won't get exactly the right solution for that first, number of meters either side of the dam wall. It's not until it propagates further downstream that the solution will be right. However, dam failures don't always fail with an instantaneous collapse of a dam wall. Sometimes you get a piping failure, which is just a gradual leak that grows and grows, and then the breach widens. So the failure mode of the dam has got a huge dynamic range of possible flow rates. Okay, so now we're on to the second case I was talking about, which is a two-dimensional model where you have a channel. You've got a reservoir at one end. You've got a dam wall with a gate. It's not a full width gate. It's only about less than a third of the width of the whole channel. It's about a quarter of the width. And then you've got a building that obstructs the flow as the flow comes out of the gate and discharges into the channel. And as you can see in the image down the bottom there, which is taken from a point in time after the breach, is you get supercritical flow coming out of the gate, and then you get a hydraulic jump in front of the building, you get a wake behind the building, you get another smaller jump in depth that's propagating to the right further down. It's quite a complex solution that you get here, and certainly there's no analytical answer for it. But what I want to point out here, hopefully this movie is coming through for you now. This is an animation of showing velocity as a function of time. The animation up the top is using a first order solution. The animation down the bottom is using a second order solution. And very importantly, both animations have no viscosity, no extra viscosity added. So the second order solution, down the bottom there, you can see is very, very detailed and rich in hydraulic jumps and vortices and vortex shedding from behind the building and wakes that wiggle back and forth like a snake's tail. Very pretty solution, but really the question is it right? What I want to point out from this animation is that the second order solution is much sharper than the first. The edges of the hydraulic jumps and so on are much better preserved in the second order solution. The first order solution looks like it's already got some viscosity in it. And that's exactly right. That's what first order does, is it adds a numerical component of viscosity to the solution. In this particular benchmark case, there were 5 gauges, depth and velocity gauges positioned around the building there, and those numbers 1 through to 5. This is just a static image that I've got at time 2 seconds or 3 seconds. The top image is when you include a sensible amount of viscosity in the solution, and the bottom image is when you don't include the viscosity. Now, again, the top image looks pretty boring and smooth, and the bottom image looks incredibly rich and beautiful. But which one of them do you think is the right solution? So what we're plotting now is we're just considering gauges 1 and 2. And I've got location 1 in the left column of plots and location 2 in the right column of plots. The pale blue dots are the experimental test result or recorded test data from the actual flume experiment. The green line is what you get out of two-flow HPC when you include a sensible eddy viscosity model. And the red line is what you get out of HPC when you don't include the viscosity. And what you can see there for both gauges is that you get a much better fit to experimental test data when you have a sensible viscosity model in there. So even though the second order solution without viscosity looked amazing, it also was wrong. So this is another reason why you've got to run these benchmarks and these tests and work out what viscosity model is going to give you the best results. And we've done a lot of work on this over the years, and we have actually arrived at a viscosity model that seems to work very nicely across a broad range of experimental sizes, all the way from lab scale to intermediate scale up to real world scale, without the user having to keep adding or adjusting terms. Okay, so that's the end of my first segment. I'll hand over to Shuang now, and he'll take you through the Malpasset Dam failure and then a whole lot of tsunami modeling work. I'll come back at the end to talk about non-Newtonian. Thank you.
Thanks very much, Greg. It's an amazing introduction, very interesting modeling result. Thanks. So in the next part will introduce a benchmarking test for real-world dam failure model, which happened to Malpasset Dam in France back in 1959. The dam collapse was caused by the rise of dam water level due to rainfall, but the dam was also called the thinnest dam in Europe at that time. Surprisingly, we actually found some video clip from that dam failure, so I'd like to switch to this one and play it briefly. And as you can see, this is a big chunk of the dam wall collapse almost instantly. And the report says that almost the entire dam wall has collapsed during the dam failure event. So it has generated 40-meter high wall of water moving rapidly towards downstream. And unfortunately, this event happened at night, so it caused mass casualty after the event. At that time, there was 3 hydroelectrical plants inside the valley, which recorded the shutdown time, so we can use that to calibrate the arrival time of the dam water. After the event, the police also conducted a field survey to obtain the flood extent. So we are going to use those 2 data to calibrate our model. For the modeling, we used 20-meter DTM and 20-meter cell size. Because the resolution of DTM is relatively coarse, we didn't apply SGS. And for the simplicity, we also used uniform Manning-Sen across the whole domain. And we calibrate the Manning-Sen from 0.03 to 0.05. The initial water level inside the dam was 100 meter. And again, for simplicity, we assumed the water was released instantly. We did the simulation in, this is a middle range GPU card, and it only took 3 minutes to complete the 4-hour of real world event. So here is the animation of the modeling result. As you can see, the dam water is recent, moves very rapidly towards downstream. And it's also hitting all of those survey points, and so it's matching the flood extent, which also indicate the height of water when it arrived at those points are also in reasonable range. The next figure shows the hydrograph at the first hydroelectrical plant. The red line is the shutdown time, and the other lines are the modeled hydrograph. Because this one is so close to the dam, so Manning-Sen didn't change the result too much. That didn't change the arrival time too much, but it did affect the maximum water level. The other 2 hydraulic electric plant is located further downstream, and as you can see, Manning-Sen have some impact on the arrival time, and at both locations, 0.04 gave a reasonable agreement between the arrival time and the shutdown time. So yeah, we are quite happy with this result, especially given that this is a historical event with relatively coarse DTM data, and we have only limited information on the bed material distribution at that time. This wraps up the dam failure benchmarking test, and in the next part, we'd like to move on to the tsunami benchmarking model. In this section, we compared our model against 2 events. One is this large-scale lab experiment, and the other was the real-world tsunami event happened in Japan back in 2011. So dam break flow and tsunami flow share lots of similar hydraulic characteristics, but what we found is very challenging in tsunami simulation is that the first thing is the source of tsunami and the receiver we want to study usually are much, much farther away. In this case, it's about 200 kilometers away from the source of the tsunami, and it took about 1 hour for the peak of tsunami to arrive at this location. And also in dam failure model, it happens usually in a constrained valley, but for tsunami, it happens in open ocean. So we usually have to create a much larger model domain, which result into much longer simulation time. So this is where flexible mesh or quadri mesh can really shine. And of course, GPU acceleration will help a lot with the simulation time. So in the next part, we would like to focus on those two parts. So the first case is a large-scale flume experiment done in Oregon State University. So they created physical model of a seaside city called Seaside. And they conducted lots of measurement, including optical measurement and velocity and water level measurement at some gauge points. And we would like to thank Dr. Park and their team to sharing the data with us so that we can carry out this benchmarking test. So for the modeling, we used two-flow HPC and quadri refinement. We applied 3 layers of refinement with only 5 centimeter grid inside the urbanized area. And then we relaxed the mesh size in the ocean side. So with this powerful tool, we can really explicitly capture those buildings with 2D cells, just increase the bed elevation. Instead of traditionally, we still use a large cell, but just bumps up the Manning sen. So this is the modeling result. And with this level of refinement, we can really get the result on street level. And as you can see, the wave is propagating, hit the buildings, and run up through those streets. So in the next section, let's compare the result with the experiment measurement. So this image, the blue dot line shows the optical measurement of the tsunami front location at a time of 26 seconds. And of course, the blue contour is the modeled result. And this is 2 seconds later. And here is another evidence that tsunami flow is highly transient. And as you can see from those white water, there's lots of hydraulic jump happening after this building and before it hits the second line of buildings. And in simulation, we also captured this, as you can see from the water depth contour. So very shallow depths here, and it became much deeper here. So there's some hydraulic jump happening here and also here. So yeah, even if we won't get this perfect in detail, but those phenomena are captured in our model. And back to the propagation area, as you can see around this street, the model produced very good agreement with the measurement, but around those 2 streets, the model result is somehow behind the optical measurement. So we took a further look at what's happening inside this street. And because in regular grid mesh, we inevitably create some mesh that acts like a vertical wall against the direction of flow. So we call this a sawtooth effect, and it will create extra artificial loss that will slow down the tsunami propagation. So in this study, we also applied the subgrid sampling. As you can see, it created some partially wet cell, and now the velocity through this street is very smooth comparing to this is non-SGS model and SGS model. And as the result, the propagation distance now is much better. Also in those 2 streets that is not well aligned with the orientation of your mesh. So we've compared the propagation extent. Also, let's look at the maximum height here at the first gauge point and the last gauge point. And again, as you can see, SGS, the pink line, will improve the arrival time significantly comparing to non-SGS model. And the maximum water level is also in good agreement. So let's move on to the next case, which is the real-world tsunami benchmarking model that happened in Japan after the magnitude 9 earthquake back in 2011. At that time, I was doing my PhD in hydraulic engineering in Japan on the day of earthquake. So I still remember that day vividly, and it was quite scary to learn about those events from the news. But that also, I think, motivated me to chase my career. And right now, I feel really privileged to be a part of a software develop team, and the software we develop can be applied in this area. So it was one of the most significant tsunami events recorded in the history. By the time the water arrived at the coastline, the wave height was from 2 to 16 meters. So this image shows this is actually a very high seawall, 10 meter high, and it was designed for 50-year tsunami event, but even that one was overtopped, and just so many water washed up the coast. And as you can imagine, it has caused massive casualty. Actually, 90% of the casualty was caused by tsunami rather than the earthquake itself. And there was several GPS buoys offshore, which has recorded the water level. And after the event, the researchers has also conducted massive field survey to obtain the flood marks from the tsunami hit area. So for the modeling, we applied TFlow FV flexible mesh modeling. And as you can see, we varied the mesh size significantly. It ranges from 10 kilometers here, the other side of the ocean, and here is the source of the tsunami. And at the onshore area, we refined the mesh to 5 meters so that we can get very detailed tsunami height there. In this presentation, I will present 2 mesh resolution models. Also, I will compare first and second order spatial scheme, and the boundary condition or the initial water level was derived based on undersea bed deformation, which was a study done by Tohoku University. And we ran the model on high-end GPU card, only took less than 20 meters to run the whole event. So again, we like to show 2 videos and ask everyone to guess which one is the first order and which one is the second order. Okay, I will just pause this one here. The one on the right-hand side, as you can guess, is the second order because it has much darker red and very sharp edge of the tsunami front, and also very sharp reflection from the coastal line. I'd like to just play this video again to show that tsunami propagate really fast in deep ocean, but it became really, really slow in shallow water, especially inside this bay area. So the next question is, again, which one is right, the first order or the second order? To answer that question, again, we have to compare the modeling result with the field measurement. And for that, we have water level recorded at one offshore GPU buoy. And we also have 5 watermarks in this urbanized area. So this is the result from the first order model. The gray one has relatively coarse mesh, and the dark blue has a much better mesh resolution. The mesh refinement, it does help increase the water level, but still it's quite far away from the modeled, the observed water level. But once we use second order model, the agreement became much better at this GPS buoy, as well as those point 1, 2, and 5. The point 3 and 4 is the first building from the coastline. So we think there are some localized wave run up. So that might cause some small differences, but overall, it demonstrates that the second order spatial scheme is really crucial to preserve the wave height in this kind of tsunami simulation, that you have huge range of mesh size. So that wraps up the tsunami benchmarking. And before we move on to the non-Newtonian part, I'd like to show some conclusion for tsunami and dam failure from modeling. So as I just mentioned, second order spatial scheme is crucial to preserve the wave height, especially in tsunami modeling. And of course, small time step is needed to capture the physics. And because those two types of flow is highly transient, so it will rarely test the stability of your model. And as Greg showed, the turbulence is very important because it's a 2D phenomena. And again, adjustable mesh and GPU acceleration is always very helpful. So yeah, we like to repeat our message that it's crucial to do a benchmarking test and just know the accuracy and reliability of your model. If that's not possible, just try to check if the model you are using is designed to model this phenomena and if they will benchmark against that. So thanks everyone. I will hand the presentation back to Greg.
Okay, thank you, Shuang. I really appreciated your inside knowledge there, Shuang, into actually having been there and experienced the fear of those around you, of the significance of those events. And like you said, it is a privilege for all of us to be able to work in an industry where we're actually about preserving human lives first and preserving our infrastructure second. Part of dam failure modeling really includes what happens when you have a dam that's absolutely full of mud, and mud is not water. Non-Newtonian fluids are fluids that don't have a linear response to shear stress as a function of shear rate. You can see the four plots there on the right there. We've got Newtonian model in the top left, and that shows a linear response of the shear stress within the fluid to the shear rate of the fluid. There's three other models that are commonly used in non-Newtonian work. One of them is the power law model, which is where the shear stress is just some power function n, exponent n, with regard to shear rate. There's another model called the Bingham plastic model, which still uses a linear response, but it has an offset, which means that it takes a certain quantity of shear force in the fluid to begin to make it shear. So this means that the fluid is actually representing a bit of a solid, something perhaps like jelly or a creme brulee or something like that. So it actually, doesn't move at all until the shear stress gets beyond a certain amount, and then it will begin to flow. The fourth model in the bottom right actually encapsulates both the power law model and the Bingham plastic model, in that it's got a power law component and it's got a yield stress component. So that's expressed in the equation that you can see there. That equation's a little bit idealized. Obviously, if n is 1.5, then you can't put in a negative shear rate. So what you do is you use the absolute value of the shear rate, you raise it to the power of n, and then you multiply it by the sine of the shear rate afterwards. And likewise, the yield stress tau 0 will flip sine for flow in the opposite direction. So you get a dead band of plus or minus tau 0 where the fluid doesn't move. Some benchmarking work. We've implemented that Herschel-Bulkley model in 2Flow HPC, and then we needed to benchmark against some real-world tests. So the first example we've got here is a laboratory scale example using Carbopol solution, paper by Couchard and Ansey, where they had basically it was a reservoir of the fluid. They would open a gate and let it flood out the gate into a puddle onto the ground outside the gate. And they would repeat this test with different concentrations of Carbopol to give different properties, as well as they would repeat the test with the whole rig on different slopes to represent a little bit of gravity acceleration with the flow or assistance. They had quite a technically challenging way of presenting the results, in that they would, on one hand, they would do a top-down view to look at the footprint or contact line of the flow as a function of time. And the other view they used is a side-on view to look at the centerline profile of the fluid as a function of time. And they would combine those two sets of results into one graph. Excuse me. So the graph you can see there on the right, the bottom half of it is the top view of the contact line, and the top half of it is the slice view or the side-on view of the center line. And you can see that there's dotted lines there marked for 0.4 seconds, 0.8 seconds, and 2 seconds. And then eventually it just comes to a stop. So the 20, 200, 2000 seconds are pretty much all in the same place because the fluid has come to a stop. It's reached its yield stress. There is a solid line on there as well, which is even more confusing, and that's the propagation distance from the gate as a function of time on the right and distance on the horizontal axis. So anyway, we've repeated this test with in modelling and simulation with two-flow HPC. We've got the we've just punched in exactly the same numbers as what they had published in the paper for their Herschel-Bulkley model coefficients with a yield stress of 78 pascals. So in this case, a shear thinning power of 0.388. It means that the fluid appears less viscous the more you work it. And what we've got there in the plots there is the blue lines represent the simulation results. Now, the agreement is pretty good. It's not 100% perfect, particularly at 0.4 seconds and 0.8 seconds, but the final footprint of how far the fluid went and its overall centerline cross-section is not too bad. The very plot on the right is when you have a downhill slope of 10 degrees for the laboratory rig. So you get a bit more gravity assistance on the flow. So you can see it's moved a bit further. And again, the final footprint's pretty good. There's some discrepancy at 0.4 seconds. We think that that is possibly due to the opening time of the gate. In the paper, the authors mentioned that it actually took them somewhere around about half a second or maybe more to physically open the gate for the fluid to move, in that basically the fluid had already reached the 0.4 second footprint mark before they had finished removing the gate. So that's possibly just some experimental difficulties there and, getting a rapid gate release of the fluid. But the agreement's there. Real world application, many of you will have seen this particular dam break in Brazil, the iron ore mine that had a tailings dam in the hill behind the mine, and it suffered really what can only be described as a catastrophic collapse. Just the entire wall of the dam just gave way in one go. Tremendous velocities as the fluid escapes and comes down, ripping out trees and everything. It really is quite spectacular. Here we've got the fluid is coming past the mine site. This is some couple of minutes after the initial burst. And what you can see there is that is not water. That is absolutely not water. That is goo. That is thick mud that's got a sharp wall on the front. It's got a yield stress. It's got high viscosity in the way that it moves. It's a very unusual material. And if you tried to simulate that particular dam break with a water-only model, you would absolutely get the wrong results. What we're looking at here is a satellite image of the dam, which is in the pink zone up in the image. It comes down the valley in this direction and flows down. It comes past the mine site, which is in here, and the railway bridge, and eventually comes down to join the river down the bottom. And this is what that looks like, satellite view after the event. So that brown color is actually where all the fluid went that came out of the dam. Obviously, it did end up going a long way. We've run a model of this particular failure using the non-Newtonian formulation, picked up the digital elevation model, which may or may not be exactly correct. It was acquired a little bit in time before the failure, and there may have been terrain changes in between time. We used a 10-meter resolution that matched the pretty much close match of the original digital elevation model. This is really one of the big unknowns when it comes to dam modeling. This is our input hydrograph that we used for this particular failure. Now, this comes out of another research paper from Lambruso 2020, who used some modeling software to attempt to calculate an approximate hydrograph that represents the breach. But in reality, I mean, it's one thing to do a hindcast where you look back and try and remodel something that happened in the past, because if you've got some evidence of what the breach looked like, then you can at least have a reasonable stab in the dark at what the hydrograph is going to be. But in terms of predicting future failure scenarios, that's a very difficult thing to do. You have to consider, well, what would a slow breach look like? What would a medium breach? What would a very fast breach look like? Or a catastrophic collapse, and present all of those possible results. Okay, in the non-Newtonian formulation, you just need the main viscosity coefficient K. You need a shear thinning or shear thickening exponent N, the power law exponent that goes into it, a tau 0, which is the yield stress. And in two-flow HPC, we also put in some viscosity limits of low and high. That's partly because the shear thinning and shear thickening power law models give some unusual results. The shear thinning model, unfortunately, diverges to infinite viscosity at near zero strain rate. So, and infinite viscosity is going to be a problem when it comes to solving the solution. So we put a clamp on the limit there. We tested a few different parameters, K of 30 to 100 Pascal seconds, N of 0.5 up to 1, and tau 0 anywhere from 400 to 4,000 pascals. Also with a high fluid density as well. It's not just water. This is tailings mud that's got a lot of, some iron ore in it. And so it's pretty high density. And we ended up settling on actually using an N of 1, which is, it is indeed Newtonian viscosity, but it's a high viscosity at 60 Pascal seconds, and also it's got a big yield stress. So what we ended up implementing was just the Bingham plastic model, but the formulation, of course, is fairly universal. What I'm showing here in the plot is the blue and orange coloured outline, of course, is the flood extent that was predicted from the final solution, and the not the dotted line, sorry, the thin red line is the observed extent from satellite images post failure. So it's not a perfect agreement up the top end where the initial breach happened, but further downstream the match is pretty good, and it came to a stop at approximately the same location as well. The solver was also, of course, the model was able to give us the arrival times for the flow as it comes down past the mine canteen and past the railway bridge. So we were able to match those fairly well. But as I said, it's one thing to do this in hindcast, but to make forward predictions, if someone's got a dam that hasn't failed and wants you to say what could happen, then, you know, what's the volume inside the dam? How much is actually going to come out with a breach? What does the breach look like? How fast is it going to collapse? And what actually are the material properties for what's in the dam? It might look like slightly solidified mud of capable of withstanding a reasonable yield stress in situ, but once it's released and that yield stress is exceeded and everything gets disturbed and mixed up, its properties are going to be quite different again. The only thing you can do is do your best to source sensible material data, do your best to interact with the client about, you know, the possible input scenarios, and present to them a spread of results. Run the model 100 times with different cases and say, you know, this was the median result, you know, this was the worst 10% of cases that went this far, and, you know, this was the best result. And it's up to them, of course, to choose what they're going to do with those. It's a very, very difficult field to be working in. You know, modeling potential collapses of non-Newtonian materials and producing sensible results for someone. It's hard work. Okay, thank you very much. That's the end of the presentation, and yeah, we'll move on to a question and answer session.
Absolutely fantastic, Greg Shuang. What a piece of experience going on there. It's so catastrophic. There's such human casualty and such infrastructure loss in these big events. I can see that you've done a lot of thinking about this, you guys, and it's fantastic. And the question and answers are going like mad at the moment. Chris Huxley will undertake the distribution of questions and answers, and so I'll hand right over to you, Chris, to manage it from here on in.
That sounds great. The question and answer line has been,
see it.
It's been hot.
How's your fingertips, Bill?
I think there's about 30 or 40 there. Yeah. Let's see. I've written down a few that I thought the broad audience might be interested in, just hearing the thoughts from the likes of Greg, Bill, and Xuan. So let me just work through those. I'll start with one which looks at more the end user of all the modelling that's done. And someone asked a question: can you provide any case studies that show prevention of loss of lives and property based on results and recommendations of modelling studies for tsunami waves? I can actually answer that based on my experience in the USA, but before doing that, I thought I'd pass over to Xuan to see if he has any experience in Japan. That's a high tsunami risk environment. Have you got any experience there? Are there Anything you can draw from?
In those conferences I attended, I've seen those researchers from uni, they use high-res tsunami modeling or street level to like decide the evacuation plan, like which street is safe, which one is relatively dangerous, and they can also add some, it's not particle tracking, but they have some particle model that will simulate how human will react to those wave height. So yeah, there are this kind of study being done, and of course, this type of model will be used to design the seawall height. So depending on the height, it's as I presented, the wave height is 16 meters. It's really high, so it's quite impossible to prevent the water from go inside the seawall. But if you raise the seawall, you can reduce the amount of water going to the land side. So based on that, they will make some decision about what's the cost and what's the effectiveness of the coastal infrastructures.
Yeah, I had a very similar experience in the USA where I was very impressed by the risk management side of things that they've done there with tsunamis. Along most of the western seaboard, I noticed there was tsunami hazard signage everywhere. There was education programs, lots to do with educating people what to do if a tsunami warning is issued. So it's very powerful, and modelling informs all that.
Yeah.
There was a few questions relating to the Oregon flume benchmark modelling. In particular, the fact that the buildings were represented within the mesh as opposed to using a high Manning's N. Bill, Greg, Shrine, can any of you sort of add some commentary as to whether one approach is better than the other, or they're both equally as good as one another? What are your thoughts?
The trend is definitely to represent them explicitly in 2D mesh just by rising the bed elevation. Traditionally, in the field of academics, we just use a higher Manning's N. That will slow down the wave propagation, but you can't go into the detail how the water propagates through a street. But yeah, of course, the uncertainty that in reality, those buildings have some certain porosity, and some building can be also washed away by the tsunami wave. So that benchmarking test is really an idealized model with solid buildings that doesn't move. So I think it's very good benchmarking model for the initial stage of your model development.
Yeah, I think the comment related to, I guess, questioning whether we're doing the right or wrong thing when we're doing floodplain modelling using that elevated Manning's N approach. And I guess my take on that is that there's multiple ways to represent different things in a model. And in that context, where you might be using larger cell sizes, it's completely fine. In the modelling Schwan did with smaller cell sizes, it's also fine.
Yeah, if you can get your cell sizes down fine enough, it's probably best to isolate the buildings. The one big exception is where you have direct rainfall modelling and you have water falling on the buildings. That makes it very tricky how to deal with it. So most models actually will model the buildings with a very, very little Manning's N, so very slippery for the roof and very high Manning's N if the water gets up and is being blocked by the building. But they definitely need SGS if you're using have cells that are crossing the boundary of the building.
That actually leads really nicely into another question someone asked, and they were looking at the same results and commented that the sawtooth effect that Schwan highlighted when SGS wasn't implemented could also be avoided by just using a triangular mesh. Is that a valid comment?
Yeah, definitely. I've done the same model with the two-floor FV, and yeah, of course, it produced a very nice result. I think each have strengths and disadvantage. I'm a big fan of flexible mesh model, but I think anyone who have done coastal modeling with two-floor FV knows it just takes massive effort and time to create high-quality mesh. So yeah, the regular grid mesh with SGS will reduce the model building time, and it can also provide reasonable results. So that's absolutely up to the users to choose which one is their preferred model.
There was a question also about hydrostatic versus non-hydrostatic. Can you describe what hydrostatic means?
Yeah, hydrostatic is, my understanding is that we assume the water is not flowing and you get just the rho GH. So the pressure is small at the top and it became larger at the bottom, which is almost a linear relationship.
Okay, very good.
Yeah, and at the beginning of dam break or when the tsunami is overtopping a building or coastal levee, of course, that kind of hydrostatic pressure doesn't exist anymore. So that's where 3D CFD software became more powerful.
Mm-hmm. Here's one I didn't know how to answer. Interested to hear views on air entrainment associated with energy dissipation for breaking tsunami waves. Any pointers or opinions, thoughts?
That's very difficult. I think there are also lots of questions about the solvers, spatial order, temporal order. What I can answer in general is that there are lots of advanced studied in university and research institution that has used really advanced mathematics and model to model wave deformation, air entrainment, even the water propagating through those porous media. But on the other side, we are rather on the commercial side, and our model is usually designed for a broader application, not just dam break, but also flood modeling or coastal. So there's always like really good model designed to pinpoint for dam break. And we always try to learn from this model, learn from the researcher to take the most advanced part to our model, and we are continuous learning. I think today's presentation shows just where we are in the industry level, and hopefully we can continue to improve in the future.
I mean, I guess I've got an opinion on that question. I'm not sure if it's right or wrong, but I'll say what my opinion is from some tsunami modeling I did for Papua New Guinea some 10 years ago. At that time, I guess I was quite junior in my career, and I always thought of tsunamis like I would a breaking wave at the beach. You know, you see these big waves and breaking. And, you know, that classic Japanese image I've got the large breaking wave. But when I did that study, I quickly learned that the wavelength of the tsunami was really long. You know, some of the waves that I was modeling had a wavelength of 30 minutes. And when I took that, or when I take that into consideration, I think about, okay, what's going to have the dominant signal on the results? And I don't think that breaking wave face would have a dominant influence in the results. It's more the turbulence and the volume of water that's sort of pushing up. I'm just spitballing there. I don't know if that's right or wrong, but I thought I'd just throw that out. Okay, I should say that all of these questions and answers will be provided with as a download next to the hosted video on the AWS website. I might leave it there.
Yep, that's been fantastic. There's just so much we could do here. We could go for hours. I can see that. But as Chris has just said, we'll attempt to get answers back to you via the website. So a recording coming to you. That's great. There's a short 1-minute survey at the conclusion. Love to have your feedback, or whack your phone in front of that QR code there and scan it, and that'll be going to the survey. That's fantastic. I think that's what we'll have to leave it there, but there's a whole lot more coming up for the Australian Water School. As you can see there, on-demand courses, 2 webinars and live courses. I think, Joel, Renee, you're going to have your work cut out. I mean, this is going to be, when do you sleep? It's a fantastic program of water resource webinars, and I can't more highly recommend it to you. It's fantastic. But look, now we're going to close off and say a big thank you to Greg and to Shuang, Bill and Chris for your excellent time today. It's been huge. Another fantastic webinar. I look forward to doing another one with you at some point in the future. So bye for now, everyone, and bye from each of us. Thanks, Bill.
Thanks, Trevor.
Chris.
Thanks, everyone.
Thank you all.
Greg.
Thanks.
Bye for now.
Bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.